Everybody knows that ordinary matter consists of protons, neutrons, and electrons. Most people know the periodic table of the elements, ordered by an increasing number of protons in the nucleus. But not many know that protons and neutrons are made of quarks. When a new particle is found by experiments in a particle accelerator, there is worldwide media coverage. Well, we've made great progress in the last decades. In 2012, for example, the Higgs boson was finally discovered. The Higgs field explains why some particles have mass, and even neutrinos, long considered massless, have a small, albeit as yet undetermined, mass. The Nobel Prize in Physics was awarded for both discoveries in 2013 and 2015. We understand better and better how the universe is built. However, visible matter only makes up a small part of the universe, and we still don't know how many dimensions there really are. To explain some of the strange observations we've made, dark matter and dark energy were introduced. The latter is responsible for the accelerated expansion of the universe, and in this video, we'll take a closer look at dark matter. Based on data from the European Planck satellite, we know that the visible matter with which we're familiar accounts for only 4.9% of all matter in the universe. 68.3% is dark energy, and 26.8% is dark matter. The idea of dark matter became known through Fritz Zwicky, 1898 to 1974. He looked at the Coma galaxy cluster, a collection of over 1,000 galaxies, in 1933, and paid attention to the red and blue shifts of spectral lines to measure the velocities of the galaxies. He found that the gravitational force was insufficient to hold the galaxies together and explained their rotational speeds. However, his colleagues at the time didn't care much for this theory, and it would be decades before it was seriously addressed. It wasn't until the 1970s that Vera Rubin and Kent Ford of the Carnegie Institution of Washington discovered more evidence for dark matter when they looked at the rotational speed of the Andromeda galaxy, M31. Dark matter, then, is matter that doesn't interact electromagnetically, doesn't emit light, and probably doesn't interact with other dark matter. It can only be seen by its gravitational influence on normal matter, and curiously, it can be used to precisely describe large-scale structures such as galaxy clusters. That's why dark matter is thought to play an important role in the formation of structures in the universe. But with the rotation curves of galaxies, it's more difficult, as if the dark matter can assume different states in different scales. The most popular theory is that dark matter consists of so-called weakly interacting massive particles, WIMPs, since these arise from hypothetical extensions of the standard model of particle physics. Other scientists favor the idea that dark matter is a kind of superfluid, an exotic quantum state. But alternative explanations also exist, with some scientists even going as far to claim that dark matter would be superfluous if you modify Newton's law of universal gravitation. They called their hypothesis modified Newtonian dynamics, MOND. However, every explanation so far has had the problem of correctly describing the processes in the bullet cluster as we know them, thanks to the Chandra X-ray Observatory. Personally, I'd find it most interesting if there were more than 3 dimensions of space, with 4-dimensional spacetime from general relativity theory. Perhaps then dark matter would be matter from the higher dimensions. What do you think? Write your opinion in the comments.